Welcome to Chapter 25, Electromagnetic Induction. We're going to be talking about, of course, electromagnetic induction, Faraday's law, generators and alternating current, power production, self-induction, power transmission, and field induction. Now, this is a curious device. You've got a magnet, a coil of conducting wire, and connect it to something to register a voltage. And if you shove the magnet into the coil, the needle will deflect in a certain direction. It turns out, if you pull the magnet out, the needle will deflect in the opposite direction. In other words, it alternates. This was discovered by Faraday and Henry, and it induces a voltage by changing the magnetic field strength in a conducting coil of wires. You shove the magnet in, you change the field strength in this conductor. In electromagnetic induction, an induced voltage can be increased by increasing the number of loops of wire in a coil, increasing the speed of the magnet entering and leaving the coil. Slow motion induces hardly any voltage at all. A rapid motion, of course, induces a greater voltage. And also, if you increase the magnet strength, too, if you use a better magnet, a stronger magnet, it's a relative motion that counts. If the voltage is induced in the wire loop, whether the magnetic field moves past the wire moves through the magnetic field. It's a relative motion between the wire and the magnetic field that counts. And this is the first step towards special theory of relativity. So here we have three coils. One has 2 loops, one has 4 loops, one has 6 loops. When a magnet is plunged into a coil with twice as many loops as the other, twice as much voltage is induced. If you have 3 times the number of loops, 3 times the amount of voltage is induced. But you never get something for nothing. It also takes more effort to do this. So you have to spend more work, and roughly 2 times the work and 3 times the work. Faraday's law states that the induced voltage in a coil is proportional to the number of loops multiplied by the rate at which the magnetic field changes within those loops. The amount of current produced by an electromagnetic induction is dependent upon the resistance of the coil, the circuit that it's connected to, and the induced voltage. Now, it's actually more difficult to push a magnet into the coil with many loops because the magnetic field of each current loop resists the motion of the magnet. It actually produces an opposing magnetic field to try to keep you from pushing the magnet into the coil. It's harder to push it fast than slowly. The faster you try to push it, the stronger the opposing magnetic field that is produced, and the harder it resists you. So there's no such thing as a free lunch. Energy is never created out of nothing. If this wasn't true, it would violate conservation of energy, and that never gets violated. When you push a magnet into a coil, you change the magnetic field inside the coil. This induces a voltage in the coil. If the coil is a conductor, the voltage induces a current in the coil. This makes the coil into an electromagnet, which resists the changing magnetic field that started the whole process. You feel this repulsion and must do work against it to continue pushing the magnet into the coil. More loops, faster push, or stronger magnet means more work. Mechanical energy is transformed into electromagnetic energy, and conservation of energy wins again. This is the big basis of an electrical generator. The resistance you feel when pushing a piece of iron into a coil involves repulsion by the magnetic field you produce. If you push the magnetic iron into the coil, you change the magnetic flux inside the coil. In response, the coil will generate a magnetic field that opposes this action because there is no such thing as a free lunch. Voltage induced in a loop requires changing magnetic fields in the loop by moving the loop near a magnet, moving a magnet near the loop, or you don't even need a magnet. You just need another current in a nearby loop. If you change the current in a nearby loop, it'll also induce a change in the other loop. Actually, the voltage is induced in the space where the magnetic field is changing. If the space includes a conductor, like a wire coil, the voltage causes a current to appear in the conductor. A changing magnetic field induces a changing electric field, which induces a changing voltage. This is the basis of electromagnetic field theory and electromagnetic radiation in light. And this is a segue chapter into the rest of the course. We'll be talking about light for the rest of the course. Applications of Faraday's law, they're around you everywhere. If you plug anything into the wall, you're using Faraday's law. Turn on a light switch, you're using Faraday's law. Your refrigerator cools your food, uses Faraday's law to do that. You got a charger on your phone, uses Faraday's law. Your phone uses Faraday's law. Everything around you uses Faraday's law. If you've ever come up to a traffic light and it changes on you, that might be an automatic traffic light. If you look down at the pavement, you might see something looks like it's been cut into the pavement. It's about the size, maybe twice the length of your car. There's a loop buried under that pavement. And your car is a ferromagnetic material. When you drive the car over that loop, it changes the magnetic field in the loop, which sends a signal to the traffic light to tell it to change. The same sort of mechanism works in security system at the airport. When you drag a ferromagnetic metal through a loop of wire, you change the magnetic field in the wire, and that sends a signal to the police telling them to pull you off to the side and say, hey, look, have you got any weapons? Scanning magnetic strips on the back of credit cards. The old-fashioned those work the same way. Recording of sound on old-fashioned tape. Old-fashioned hard drives. Those are all use Faraday's law. Okay, your cell phone uses Faraday's law. All of these things, anything you talk about, anything your computer uses it, it's full of this, is everywhere. More voltage is induced when a magnet is thrust into a coil more quickly. It's sort of hard to get both A and B. How would you get both A and B? That's kind of a funny question. Not only is voltage induced when a magnet is thrust into a coil of conducting wire, but if it's a conducting wire, you also get current. And of course, you never get more energy output. There's no such thing as a free lunch. A generator is basically the opposite of a motor. A generator converts mechanical energy into electrical energy via coil motion. It produces an alternating voltage or current. If it's wired differently and filtered, it can produce direct current. All generators basically produce alternating current, and all they do is they filter it and wire it differently to make it direct. Now, here's the difference between a motor and a generator. A motor and generator are basically the same machine, just run in reverse. A motor converts electrical energy to mechanical energy. What's going on in a motor, you have a magnetic field and you have current flowing through the wire. And when the current is turned on, the wire deflects because the moving charge particles in the wire interact with the magnetic field, and that causes a force on the charge carrier in the wire, makes the wire deflect, converts electrical energy into mechanical energy. The generator works the opposite way. If you move a wire, a conducting wire in a magnetic field, it creates a magnetic force on the charge carriers in the wire. The force moves the charges along the wire, generating a current. In this case, mechanical energy is converted to electrical energy. So here is an AC generator. All it is a loop rotating in an external magnetic field, represented by these green dotted lines. And every time this thing turns, it changes the amount of magnetic field lines that are going through the loop. This changes the magnetic field in the loop, which induces a alternating voltage in the loop. And every time this thing turns, the voltage switches. So here's positive, negative, positive, negative. This is a sinusoidal output. It's a sine wave. And the positive, negative is the alternating part. It alternates polarity. That's what AC actually means. Now, this uses Faraday's and Henry's discovery of the electromagnetic induction. Nikola Tesla and George Westinghouse ran with this and showed that electricity could be generated in sufficient quantities to light cities. And that's where we are today. That's where we have a power grid. That's why you can turn on a light switch. You don't have to light an oil lamp. This is another type of generator called an MHD, or magnetohydrodynamic generator. This eliminates the spinning coil and whatever is driving it. Okay, and the spinning coil is called an armature, and usually we're driving it with a turbine. So it eliminates those two things. What they do is they inject a plasma of electrons and positive ions. So they expand it through a nozzle, and of course then it moves at supersonic speeds through a magnetic field. The magnetic field will deflect the particles. The particles of one sign will go to one side. The particles of the opposite sign will go to another side. That causes a voltage to appear across these two plates. If you connect that potential difference or voltage across the load, like a resistance, a current will appear. So basically, this motion of charges through a magnetic field induces a voltage and flow of current as per Faraday's law. Now, you probably have these things in your house and you don't even realize it. Okay, you're probably using a computer or a cell phone and it's got a charger. There's that annoying, chunky, blocky thing in the middle of the power cord. It's all that you're always tripping over. That is a transformer. All right, so what it is basically all it is two coils of wire wrapped around a common iron core. The side of the wire that you connect into the wall is connected to a primary coil, primary for being the first coil. The other side that you connect into your computer is a wire that connects to a secondary. That is the load. So the primary has the AC input, the secondary is the load, connected to the load. Now what's inside a transformer? Basically what it is two coils of wire, primary and secondary, wrapped around a common iron core, and the common iron core enhances and contains the magnetic field so it all stays in the primary and the secondary. It uses an alternating current and voltage in one coil to induce an alternating current and voltage in the second coil. If the current doesn't change, this doesn't work. So in other words, if you connect this up to DC and try to put DC through this, the DC won't come out. Now, step-uppers can step up or step down voltage. A step-up transformer produces a greater voltage in the secondary than is supplied by the primary. The secondary, therefore, has more turns in the coil than the primary does. So this, say you want to take 120 volts and make 1200 volts out of it. You would run it through would have maybe, 100 turns in the primary. The secondary would have 10 times as many turns or 1,000 turns. And that would step up the voltage from 120 to 1200. A step-down transformer does just the opposite. It produces a smaller voltage in the secondary than is supplied by the primary, so the secondary has fewer turns in its coil than the primary coil does. So suppose you have 120 volts and you want to step it down to 12 volts. You might have 100 turns in the primary. You'd have only 10 turns in the secondary to get that 10-to-1 reduction. An isolation transformer has the same voltage in the secondary and primary coil, so it has the same number of turns in either one. What is this useful for? Well, it's used to clean up dirty voltage. Remember I told you that transformers do not transmit DC. If you have some sort of contaminated voltage that maybe has AC and DC in it and you want to get rid of the DC, you run it through a transformer. The AC will come out, the DC doesn't go anywhere. You can also wire it in another way to get rid of the AC and keep the DC. Okay, so transformer relationship. You knew this was coming. Primary voltage divided by the number of primary turns equals the secondary voltage divided by the number of secondary turns. A transformer transfers energy from one coil to another. The rate of energy transfer is power. Power into the primary equals power in the secondary. So voltage times current in the primary equals voltage times current in the secondary. Now we're assuming 100% efficiency. Actually, the power in the input is generally greater than the power out due to losses. Where the losses come from? Primarily heating in the coils due to resistance in the wires. This will affect the current outputs rather than the voltage. So in other words, there would be voltage times current in the primary equals voltage times current in the secondary plus any losses. Now, transformers basically transfers the energy from one coil to another. And for example, we might have voltage stepped up before leaving a power station. Okay, and then it gets transmitted over very long distances, a high voltage, low current, and then it gets stepped down for distribution near cities by cables that feed the power to the grid. And then again, they step it down again before being supplied to businesses and consumers through substations. We'll explain later why they do this. It sounds sort of weird, doesn't it? We'll explain later why they do this. By the way, you've probably driven by one of these on a pole. Next time you go past poles, look up carefully. Please do not do any distracted driving. If you notice one of these, that is a transformer. A step-up transformer in an electrical circuit can step up voltage. It will not step up energy. An efficient transformer in AC electric circuit can change current. Current carrying loops in a coil interact not only with the loops of other coils, but also with the loops of the same coil. Each loop in a coil interacts with a magnetic field around the current in the other loops in the same coil. This is called self-induction. When a switch is open, the magnetic field of the coil collapses. The sudden change in the field can induce a huge voltage. This can be dangerous and destructive. This is why you buy surge protectors, because this causes surges in wirings connected to large motors. So think of how many large motors are probably in your house. If you have a refrigerator, you've got a large motor. You have an air conditioner, you have a large motor. The blower in your furnace is a large motor. You have a well pump, that's a large motor. All of these things can cause surges in the wiring. You should never turn off appliances by grabbing the plug. If you notice a really large spark when you pull something out, like a refrigerator that's running, that's what you've done. You've interrupted the circuit, caused the magnetic field to collapse, and induced a huge voltage. Do not plug sensitive electronics into the same circuit with appliances such as air conditioners, refrigerators, or large motors, because they will slowly, every time those things turn on and off, they will start destroying your sensitive electronics. Connect all sensitive electronics to surge protectors and make sure your wiring is properly grounded. Surge protectors don't work unless the wiring is grounded properly. And I promised I would do this. Why do we have this complicated thing? Well, almost all electrical energy sold today is in the form of AC because of the ease with which it can be transformed from one voltage to another. Think of a transformer. It's simple. It has no moving parts. It's low maintenance. And you can leave it out in the middle of nowhere forever, and it still works. Okay, so what do? Large currents and wires produce heat and energy losses. Remember the I squared R loss? It's I squared. You double the current, you have 4 times the energy loss just due to heating the wires. So what they do is they pop up the voltage really high because power is current times voltage. If you can keep the voltage high for given power, the current is relatively low. So they transmit power at great distances at very high voltage and very low currents to keep that I squared R loss down. The power might be generated if 25,000 volts or less in the power station. because it's safer to generate a low voltage. And then it's stepped up near the power station as much as 75,000 volts for long distance transmission. And then they transmit over very long distances, keeping that current as low as possible to keep that I squared R loss down. But eventually it gets to someplace like a substation. And then we have to get it back to where it's safe again. So what they do is they step it down at substations and distribution points. The voltage is needed maybe in industry, 1,000 volts or 440 volts, and for the home, 240 and 120. The lower voltage is safer. You wouldn't want 750 kilovolts in your house. That'd be very dangerous. So electromagnetic induction is actually a two-way street. Faraday's law states that an electric field is induced in any region of space in which a magnetic field is changing with time. Maxwell says that a magnetic field is induced in any region of space in which an electric field is changing with time. So a changing magnetic field induces a changing electric field, which induces a changing magnetic field, which induces yada, yada, yada. And that is an electromagnetic wave. Did you realize that 120 volt that you plug into the wall outlet, you plug your computer charger into the wall outlet, that 120 volts is an electromagnetic wave. It's basically the same animal as the light wave is, as your radio waves are. All of those are basically the same animal. The mutual induction of electric and magnetic fields can produce light. All electromagnetic waves are mutually induced electric and magnetic fields. We will discover more of this in later lectures. This is sort of one of those segue chapters. Light is produced by the mutual induction of electric and magnetic fields. The speed of light is the speed of the emanations of these fields. And it's a very specific field. It's one of the fundamental physical constants. If the electromagnetic radiation tries to go too slow, the regenerating fields die out. The electric field and the magnetic field don't self-induce each other. If it tries to go too fast, the fields build up, and that would violate conservation of energy. There's one Goldilocks speed that's just exactly right, neither too fast nor too slow. You wind up with light. Voltage will be induced in a wire loop when the magnetic field within that loop changes. When you thrust a bar magnet to and fro in a coil of wire, you are making AC, which is an alternating voltage, which if it's a conducting loop, will produce an alternating current. When a magnet is moved into a wire coil, an induced current in the coil produces a magnetic field that resists the motion of the magnet. So the more coils or the faster you push or the stronger the magnet, the more it fights you. There's no such thing as free lunch. You have to do more work. Faraday's law is actually, this was kind of a tricky question. It's a law of energy conservation as applied to electromagnetic induction. So specifically, it's a law of electromagnetic induction resulting from energy conservation. The underlying physics of the electric motor is that a current carrying wire experiences a force in a magnetic field. So in other words, it is a changing of electrical energy into mechanical energy. The essential physics concept in an electrical generator is, of course, Faraday's law. Within both a conventional ammeter and voltmeter, you will find a galvanometer. Both a motor and a generator operate via similar concepts. The major difference between a motor and generator is input and output. In other words, they're just reversed. So a generator converts mechanical energy into electrical energy. A motor converts electrical energy into mechanical energy. When a generator is used to light a lamp, the energy of the lit lamp originates in the work done to turn the coils in the generator. The purpose of a transformer is to transform power at one voltage to the same power at another voltage. A transformer works by way of Faraday's law. A step-up transformer in an electrical circuit will step up voltage, not energy. A step-down transformer has a greater number of coils in the input side and fewer number of coils on the output side. And the ratio of input to output will also give you the ratio of voltage. The working of a transformer is consistent mainly with conservation of energy. To minimize heat losses for power transported across the country, it's best that the current be very low because power is resistance times current squared. If you make 1/10 of the current, you have 1/100th of the power lost. Lighting a lamp via electromagnetic induction requires work input. You never get something for nothing. You have to pay your electric bill. By the way, the power company sells you energy, not power. Kilowatt hours, which is a unit of energy, not power. A changing electric field can induce a changing magnetic field, according to Maxwell. If you change the magnetic field in a closed loop of wire, you induce in the loop all of these, a current, a voltage, and electric field. The fact that electric and magnetic fields regenerate each other is important in any electromagnetic wave. And of all of those, radio broadcasting is an electromagnetic wave. Thank you.